Hello and welcome to this pre-lab video. This is the pre-lab for V12, the virtual lab for buffers. Now this lab will be split into two parts, or excuse me, rather this video will be split into two parts. The first part here is going to be covering mostly the pre-lab for this particular virtual lab and maybe a little bit of the procedure and some of the walkthroughs for how to do the simulation. We're going to spend most of the time talking about the concept of buffers and getting into those pre-lab questions. The second video, which will come out at a later time, will cover more extensively that actual simulation and talk more about the post-lab because the two concepts are actually different. The pre-lab is going to be talking about one particular facet of buffers, and the post-lab is going to be talking about a different facet of buffers. So before we get too deep into the differences between the two, let's talk about what these things are. So what is a buffer? By definition, a buffer is a solution that contains two things. Those two things are a conjugate acid-base pair, meaning I've got a weak acid and its conjugate base, or I've got a weak base and its conjugate acid. But the key aspect to this is that it has to be a weak pair. So we're not going to see buffers with any kind of strongs. No strong acids, no strong bases. The resulting conjugates are not reactive enough to actually do buffering. But what this pair does is because they essentially can interconvert in between each other, they make the solution much more drastic in terms of its resistance to pH. Now, buffers themselves are the result of something called the common ion effect. Common ion effect is something that you saw at the beginning of this chapter, chapter 16, and it's a relatively simple premise. The premise is something along these lines. I've got an equilibrium system. There's my equilibrium system. The dissolution of ammonium chloride, which is a pretty robust solution, has a really high K value because ammonium chloride is really, really soluble in water. However, if I add additional chloride ions to the solution through, say, making the solution in sodium chloride instead of pure water, Le Chatelier's principle tells me that the addition of that extra chloride is going to cause a shift that is going to force the equilibrium to the left toward the reactant, which means that my ammonium chloride is going to be less soluble in sodium chloride than it was in pure water. So that's what the common ion effect is. The common ion effect says I have an equilibrium and I get introduced to a common ion, something from the outside that happens to share an ion with my equilibrium. That extra ion is going to impact the equilibrium that I'm interested in. And so where we get some of this kind of concept is we can see it kind of in our everyday lives. For example, blood. Your blood is a buffered solution. The buffering in your blood keeps it at pH 7.4 or so. You've got a combination of the carbonate ion and carbon dioxide in the blood. Seawater is also a buffered solution, where you've got a number of different compounds that are dissolved in the water as part of the salts. And it allows the pH of the seawater to be in that slightly basic range, which is great for things like fish and mussels and crustaceans and seaweed and a whole bunch of other stuff, and allows it to be useful. Buffered aspirin, bufferin. The buffering in that acid is to negate some of the effects of aspirin itself. Aspirin is a derivative of an organic acid, acetyl salicylic acid, and um, in certain kinds of patients, it can really be kind of damaging on their stomach, because if you have a really sensitive stomach to acid changes, aspirin can be really difficult. So the buffering in that particular supplement allows for the patient to absorb the aspirin in a much safer, better manner. So here is a pictorial example of buffers. And so what we can see here in this example is that our middle panel here, this is the buffered solution. In this buffered solution, we have equal concentrations of the weak acid shown here in blue and white, and its conjugate base, the blue negative ion here. And what's interesting about this is right now that pH is set at about 6.5. If I add some acid to this, what happens is that some of those negative ions grab onto the extra hydrogen that was brought up by adding the acid. Remember, adding acid adds H+. And so one of these picked up an H+ and became an acid molecule. As a result of that conversion, well, we see that the pH did get more acidic, but slightly so. If this was pure water, we would see a much more drastic change in the pH, because there would be nothing there for the hydrogen to hold on to other than water molecules, and the water molecules form hydronium, which drops the pH. On the flip side, adding base would add hydroxides. Hydroxides in this case would steal hydrogens from the conjugate acid, leaving behind an extra ion. And so as a result, we do see that the pH does tick up toward being more basic. But again, if this was pure water, we would see a much more drastic change, because there would be nothing to counterbalance that hydroxide being added. And so that's really kind of the power here of a buffer, is being able to see that it doesn't change pH considerably, but pH is going to change, and it's going to be changing based upon the relationship between that conjugate acid and that conjugate base. So how does it work? Well, I want you to consider this particular conjugate system. So I've got carbonic acid in solution with sodium bicarbonate. So I've got my acid and its conjugate base both here, both present at the same time. How does it ultimately resist pH changes? Well, we have to take a look at each part individually. When an acid is added, that conjugate base reacts with the H+ to turn back into the acid. And so all that has happened is that the concentration of the carbonic acid has increased, whereas the concentration of the bicarbonate ion has decreased. We haven't seen a really drastic change in hydronium or hydroxide, so the pH is going to be relatively well regulated. What does that mean in terms of the equilibrium? Well, again, we see a downturn here and an upturn here. We know from our Le Chatelier's principle that an increase in the reactant or a decrease in the product is going to have a net effect of shifting to the right toward the products. We'll end up getting more hydronium, not much, but more hydronium, and that is going to decrease the pH, but by a lesser extent than what this hydrogen would have done by itself in water. When we add base, it's kind of the opposite effect. Instead of looking at the conjugate acid, or I'm sorry, the conjugate base, we're going to look at the conjugate acid. So here's my acid, carbonic acid, and we can see that the acid plus the hydroxide is going to give us the conjugate base plus water, where the hydroxide is taking one of those hydrogens off of the acid to form water, and we're left behind with that conjugate base. Net effect here, we see that the concentration of the bicarbonate ion is going to increase. The concentration of the carbonic acid is going to decrease. So I've got a decrease here and an increase here. Chatelier's principle tells me I'm going to see a shift to the left, which means hydronium concentration is going to go down slightly, which means the pH is going to go up slightly. Here's another example using hydrogen fluoride and fluoride ions. Again, starting with our initial conditions where we have roughly equal amounts of each one. I add hydroxide. The hydroxide reacts with the hydrofluoric acid. I end up getting more fluoride ion as a result. And so all that really changes is, instead of the two being even, so here we started with even concentrations. Now we're going to see slightly changed ratios of one to the other. And on the acid side, acid is going to react with the fluoride to give us more HF. So here, the concentration of the hydrofluoric acid ends up being larger than the fluoride. Again, we see a minor change in pH, but not a terribly drastic one. We can quantify all of these changes using something called the Henderson-Hasselbach equation. Henderson-Hasselbach equation tells us that the pH of a particular solution, a buffer solution in particular, is related to the pKa. This is the pKa for the conjugate acid, or the weak acid, whichever one you want to look at, plus the ratio of the log of the base over the log of the acid, or put in more simple terms, the ratio of the base concentration over the acid concentration. So this is how we can quantify those minor changes in pH based upon how the base concentration changes versus the acid concentration changing. Minor changes, yes, but something significant enough that we'll notice it without it completely going one way toward acidic or one way toward basic. So some key features of this Henderson-Hasselbach equation. First of all, when the base and the acid are equal to each other, which is kind of what we've been starting with for those scenarios that we just outlined. When that is the case, base and acid are equal to each other, then we end up doing the logarithm of 1, and the logarithm of 1 is 0. So in that scenario, the pH and the pKa are equal to each other. We've talked about this particular scenario a number of times. This is what the half equivalence point in a titration is all about. When we hit that half equivalence point, we have equal amounts of acid and its conjugate, and therefore the pH and the pKa are the same. When they're not the same, when the base is higher, we end up getting a value here that is greater than 1. And so as a result of that greater than 1 pH, that greater than 1 logarithm, this is going to tick up slightly. The pH is going to be slightly above pKa. When the acid is the dominant species, as in the case when we add strong acid, our pH, or excuse me, our logarithm here is going to dip below 1, which means that this is going to be a negative value, and the pH is going to be slightly below the pKa. Now, one important note about the Henderson-Hasselbach equation, again, the particular equation is acid specific. So pH is equal to pKa plus the log of the base over the acid. There is another form of this equation that is particularly useful if you have a base. And it's basically the same equation, only flipped on its head. So for POH, POH is equal to the pKb for the weak base, plus the log of the acid concentration over the base concentration. So when you deal with buffer solutions where the weak component is basic, this is one way to use that and not have to do a whole lot of maneuvering. Now, the other way to do it is you can turn that pKb into a pKa using this equation right here, and that works just as well. It's kind of the same idea, because ultimately we're going to find pH by taking 14 minus POH. So whether we use this form or the previous form, basically we're going to do the same two steps. It's just a matter of which order do we do them. Do we do the subtracting by 14 to figure out the pKa and then use the Henderson-Hasselbach equation in its acidic form? Or do we use the Henderson-Hasselbach equation in its basic form and then convert the POH to pH by subtracting it from 14? It's kind of two ways of doing the same thing. It's just a matter of, kind of what your preference is. So let's take a look at a problem here. What is the pH of a sample of river water in which the concentration of the bicarbonate ion is 1 times 10 to the negative 4th molar, and the concentration of the carbonic acid is 1.4 times 10 to the negative 5th molar? Well, there's some information that we're going to need here. We're going to need either the Ka or the pKa for carbonic acid, which is the acid derivative of carbon dioxide. So carbon dioxide plus water gives us H2CO3, carbonic acid. So that's the first part that we need. After that, it's pretty smooth sailing because this is really just the Henderson-Hasselbach equation. We've got our base concentration here. We've got our acid concentration here. We just need to figure out this missing piece. And to find that missing piece, I'm going to need to do a little bit of moving and digging. What we need is a reference. We need a value of Ka, and so a reference table is going to be where we get that. Reference table in your lecture packet tells us that carbonic acid has a pKa, or excuse me, rather a Ka of 4.4 times 10 to the negative 7th, and so that's what we're going to use, 4.4 times 10 to the negative 7th. So setting up the Henderson-Hasselbach equation then, pH is equal to pKa plus the log of the concentration of the base over the concentration of the acid. pKa, negative log of 4.4 times 10 to the negative 7th plus the logarithm of the base concentration, which was 1 times 10 to the negative 4th, over the acid concentration, which was 1.4 times 10 to the negative 5th. So getting out your calculator here, the pKa, 4.4 times 10 to the negative 7th, log of that is 6.36 for carbonic acid. 1 times 10 to the negative 4th divided by 1.4 times 10 to the negative 5th is 7.14 for for this value here inside of the parentheses. The log of that is 0.85. So that means that the pH is equal to 6.36 plus 0.85, which would be 7.21. So at a pH of 7.21, that river water is actually, doing pretty good. It's a little bit higher than seawater, but it is, it's not terribly acidic. In fact, it's not acidic at all. It's slightly more acidic than your blood, so I mean there would be some concern there potentially, but not a significant amount. All right, let's look at another one. Determine the pH of a buffer made by combining 0.45 moles of sodium acetate with 0.25 moles of acetic acid and enough water to make 1 liter of solution. So a little bit more work to do here. We've been given a Ka value, so we need to turn that into a pKa. So the negative log of 1.8 times 10 to the negative fifth is 4.74. So that is my pKa for the acetic acid. The other things I need the concentration of the acid and the concentration of the base. Now, in this case, it's pretty easy because we've got 1 liter of solution. So 0.45 moles of sodium acetate divided by 1 liter, so give me 0.45 molar. Again, this is for the acetate. The acetate is the conjugate base. And that would mean I'd have 0.25 molar for the acetic acid, which would be my acid. So pH is equal to 4.74 plus the log of the base, 0.45, over the acid, 0.25. The sum here is, or excuse me, the quotient here is 1.8. Log of 1.8 is 0.26. And so that means the pH of this particular buffer is 5.00. All right, so that covers kind of the introductory concept of buffers and how we can determine the pH of a buffer. But what if I wanted to make a buffer? What if I wanted to make a buffer of a particular pH? Well, that's a little bit different. We're going to use the Henderson-Hasselbach equation to do this, mind you, but we're going to have to use it a little bit differently. And we're going to have to set some parameters. How much of this buffer do we want? And once we establish that, how do we go about getting it? What quantities do we have to mix up together to do it? So let's take a look at this particular example. And this will speak to something that you're going to see in the pre-lab. You are asked to make a cinnamic acid cinnamate buffer. Has a pH of 5 from 50 milliliters of 1 molar cinnamic acid, which is a pKa of 4.440. How many grams of sodium cinnamate would you need to add to the solution to get it to that pH? We're going to make the assumption, it's probably a bad one, but we're going to make the assumption nonetheless that there's not going to be a change in the volume as a result of adding this acid or this solid. So how do you go about doing this? Well, we have to take into consideration what information we do have already on hand. And we do know from this standpoint that we do have a pH of 5 and a pKa of 4.40 or 4.44. So from the Henderson-Hasselbach equation standpoint, that's 2 of the key components right there. I know the pH, 5.00. I know the pKa, 4.440. The thing I don't know yet is this ratio of acid and base. And I'm just going to leave that as it is right now because, well, we're kind of missing something. We don't know exactly what we need to do. But I can solve out kind of the rest of it. So if I do the subtraction, I'm going to end up with 0.56 is equal to the log of the base concentration over the acid concentration. Again, I'm just going to leave that in big, broad terms. To get rid of the logarithm, I need to take the anti-log of both sides. So 10 to the log is going to give me B over A over here. 10 to the 0.56 is going to give me 3.6. Try that again. .63 over here. Now, how do I interpret this? Well, that means that the concentration of the base is going to be 3.63 times the concentration of the acid. Now, we've been told that the acid is going to be 1 molar, which means that the concentration of the base is going to be 3.63 times that. It's going to be 3.63 molar in its concentration. How do I turn that into a mass? Well, I've got to use my solution characteristics. And for that, I need to know molarity times volume will give me moles. And then I can convert those moles into grams using molar mass. So I've got 50 milliliters, that's 0.05 liters, multiplied by 3.63 molar, and that would give me 0.182 moles of sodium cinnamate, C9H7O2 Na. If I multiply that by the molar mass 12.01 for the carbon times 9 plus 1.01 for the hydrogen times 7 plus 16 for the oxygen times 2 plus 22.99 for the sodium is 170.15 grams per mole, which means times that 0.182 moles, we're talking about 31 grams of the sodium cinnamate. So, like I said, kind of in the introduction here, this is not going to occur without changing the volume a little bit. It's going to actually change it significantly, but we made that assumption and we're just going to run with it. The real key to these kinds of problems is trying to keep it as simple as long as possible, and that's what this was all about, and then interpreting the results correctly. So once I interpreted the results and figured out, okay, this is what my concentration needs to be, and this is how I'm going to go about getting it, it wasn't really all that difficult of a problem to do. I just had to lay it out appropriately, lay it out correctly. And so where we want to go from here is we want to look into lab archives and see, okay, what is it that we are asked to do? So here, what is the pH of a buffer solution that contains 1.12 molar formic acid and 11.1 grams of sodium formate? Total volume of the solution is 125 milliliters. Here is my Ka information. Well, this is relatively straightforward. This is just Henderson-Hasselbach equation. I just need to do one thing before I plug those values in. I need to turn this into a number of moles. And then I need to divide those moles by the total volume to give me the molarity. Once I have that, that molarity is going to be my base concentration. This is my acid concentration. And this I will need to convert into pKa. And then that's all I need. That's all three components right there. The second question here is the one that's a little bit more involved, a little bit more difficult, because it's the same kind of question as that cinnamic acid question. I need to make a pH buffer of 3.5. This time I know what concentrations I'm going to use. I just need to know what the molar ratio is. And so, excuse me, the nice thing about this particular problem is that part's already been kind of set up for you. Part A just wants to know what is B over A. So I've got my pH. I've got my Ka, which I'm going to need to convert into a pKa. And I'm eventually going to need to turn it into this ratio. So very similar to what I did, I'm going to take 3.50 minus the pKa rather. That's going to give me the log of the base over the acid. And then if I take the anti-log of both sides, I would get just B over A. From there, now it's where it gets a little bit more interesting. It hasn't given us a set volume. And that's okay that it hasn't given us a set volume. What's nice is that this particular ratio can tell us either the concentration ratio, but since the two concentrations are the same, it's going to give us also the volume ratio, but in reverse, because we're looking at B, concentration of B over concentration of A in terms of what they are relative to each other. What we really are looking for here are moles. And so if I can figure out how many moles of B I need relative to the number of moles of A, what I would do from there is just set an arbitrary value. I'm going to make 100 milliliters of the solution. If 100 milliliters are necessary, how many moles of B do I need? How much of the solution do I need to give me that many moles? How many moles of A do I need? How much of the solution do I need to get me there? That's the way to handle this one. And so that's where we're going to stop this video, is at the end here with our pre-lab assignment. Again, there's another video coming here with how to do the actual procedure, and this is important, how to handle those post-lab questions. So, we talked in the kind of conceptual framework. Here's what happens when an acid is added. Here's what happens when a base is added. The post-lab questions actually get into calculating what should happen to the pH when we add that acid or when we add that base. And that's a calculation that's a little bit more involved than just simply using the Henderson-Hasselbach equation, although we will end up ending all of those calculations with the Henderson-Hasselbach equation, just like we did here. So until then, have a good day, and I will see you in lab.